Hello, my name is Margarita Rebolledo, and I will present the core ideas of our work, Impact of Energy Efficiency on the Morphology and Behavior of Evolved Robots. We want to study the energy efficiency on evolvable robots. In this case, they can evolve the body and the controller. We want to discover which are the dominant body shapes. We start this with an hypothesis, and we think this will result in the smaller robots with the same speed as the robots without the energy included in the fitness. Or we will have faster robots with the same size. We have two main research questions. The first one is, how does the energy use affect the behavior of the evolved robots? Or how does it affect the morphologies? The system that we use to simulate the robots is a combination of GECCO and Rebolledo. You can find it under this link. We define two objectives. The first one is the energy consumption of the robots. In this case, we only count the joints that the robot body possesses. And we define an initial charge. Once this charge is depleted and it goes to zero, then the simulation of the robot will stop. If the robot doesn't move, the simulation stops either way after some defined time. The second objective is the speed, and this is defined as the difference in the final position and the initial position of the robot divided by the time. For experiments, we have two experiments, the baseline experiments, where only we use the speed as the only objective, and the battery experiment when the speed and energy are both the objectives we want to optimize. For this, we use the NSGA2 optimizer. For the robots, we want to limit the size, so we allow robots to have only a maximum of 10 joints and 20 bricks. We define our initial charge. For the evolutionary round, we define a population of 100, and the same goes for the offspring and the generation number. And we repeat these experiments 10 times for statistical significance. We can check here how the robot that we use look like. These robots are formed from three different components. The first one is the core component, here the yellow. Here is the battery and the brain, the controller of the robot. The blue components indicate bricks. These are used for connections. And the red ones indicate the joints. In each joint, there is a servo motor that can move the robot. And these are the only ones that we consider for energy consumption. There are here two samples of robot morphologies. The first one is from the battery experiment, and the second one is from the baseline experiment. And here we can see that the difference in the size of this robot is quite considerable. We can focus on the distribution that these robots have in terms of their number of joints and their speed. We define a threshold, and robots above this threshold are robots that we say are good or fast enough. There are here a lot of robots in the battery experiment that do not move. This is because NSGA also finds the really battery efficient robots, in this case a robot that has no joints and cannot move. If we consider only the robots that go above the threshold, we can see that in the battery experiment we have a total of 71 robots, and in the baseline we have 940 robots. If we check the mean speed of this set of robots, we can see that it's quite similar, and we can also say that it is not significantly different. We can answer our research questions, and we can say what is the effect this energy inclusion in the evolution round has, is that the lower median speed of the robots is lowered, and it has a higher spread. But it is possible to have a small size robot with high speed. And how does it affect the morphology? We see that there is a reduction in the joints. And we see, however, that for both experiments, we have as result snake-like morphologies. As an overall discovery from our study, we can say that the robots of the same size can be faster when energy consumption is part of the evolution.